Right, everybody, 8 o'clock. Welcome back to my guest bedroom. That's right. Okay, a couple of announcements really quick. First, I did grade your homeworks, so you should be able to see on Blackboard now your homework grade. And I also posted my solution for the homework. So if you were having some struggles on homework number one, make sure you take a look at the solution and kind of understand what's going on there. Reminder, I did post all the notes for 429. So those are available on the lecture notes page. So if you want to kind of like refresh, how do I do micro failure theory, or how do I do transformations, or whatever, really suggest you kind of go there and kind of refresh yourself all these things that we did in 429. Okay, they're going to be even more important as we move forward, since we're going to sort of be building on those things at least for the next couple of weeks as we get into laminate failure theory and some of the other kind of complicated laminate stuff that we have going on in the class. Okay, so that's homework number one. I posted a new homework number two, and it is very MATLAB heavy. Okay, so I'm asking you to write some user-defined functions. So I have some notes on there that I've uploaded in case you kind of forgot what that means or how to do that. User-defined functions for things like how to calculate the ABD matrices, how to calculate a Q matrix from inputs of material properties and laminar properties. So these are functions that maybe you have already written, or you have definitely executed them in MATLAB with probably 90% certainty. So writing the functions shouldn't take all that long, and they will be very helpful once we get into the more computational intensive portion of this class, which is when we get to laminate failure theory. Okay, laminate failure theory, complicated. All right, you got to figure out the stresses in each particular layer. You have to analyze every single layer. I'm telling you, you don't want to do that by hand. So I'm sort of prepping you right now by forcing you in this upcoming homework to write some functions which are going to be very useful for you once we get to that portion of the class. So a little bit longer on the homework this time around, but bite the bullet, get it done. It'll stop you from going outside. Okay. So that's that. Okay, I think that's kind of all the announcements I have for the class. I did start the recording this time, so yay me. We'll pick up the discussion then with where we ended last time. So last time, just as a quick reminder, I'll pull this up. I can do it. I can do it. Yay! All right. Last time, as a reminder, we were talking about the relationship between loads that we apply on a laminate and the resulting stresses and strains. So we derived equations for the relationship between, of course, this is not working, never works. Turn it off, turn it back on. Fix all. We were talking about relationships between applied loads, here represented by a vector n, and the resulting strains. I don't know why that just jumped down there. And the resulting strains and curvatures, which developed here. And additionally, the moments here, and the resulting strains and curvatures that developed. All right, so we wrote this in shorthand to kind of tighten things up, as the applied loads are some combination of the strains that develop and these sort of stiffness matrices. We're writing in shorthand A and B, and the moments that develop related to the strains and curvatures that applied through stiffness matrices B and D, where we had defined B and D using some kind of complicated sort of looking equations here. Summations of the stiffnesses that are contributing of each one of the individual layers. So here we're summing over all of the layers in the laminate their individual contributions to the stiffnesses, given things like the geometric parameters of these guys, denoted by the thicknesses z or z squared or z cubed. Here, this is the stiffness of each individual layer, and we have some coefficients that might hang out in front. All right, so this is kind of where we left off last time. And all together, written in matrix form, was something like this. All right. We talked about the actual physical interpretations of what these matrices are, and we talked about the A matrix being the relationship between longitudinal loads that I might apply and longitudinal strains which might develop. All right, so this is sort of like the stiffness that you're very familiar with. Like if we load something longitudinally, the stiffness of that thing is how much it resists deformation in that direction. Sort of makes sense. All right, another intuitive stiffness is the D matrix, which is the relationship between how much bending moment we put on a laminate and the resulting curvature that occurs. All right, the higher the numbers in the D matrix, the more moment I have to apply to create the same level of curvature. All right, so a stiffer or a higher D matrix indicates that it's harder to curve the laminate given an applied bending moment. And then this B matrix, which was sort of the strange one that arises with orthotropic materials, composites, is the one where if I pull on the laminate, its tendency to curve. All right, so it's this coupling effect between longitudinal applied loads and what curvature might come out from applying these longitudinal loads. All right, there's also that stiffness matrix relates the bending moments that I apply to longitudinal strains which might develop. So very strange matrix that really is unique to composites and composite laminates, that we can apply longitudinal loads and have curvatures, or we can apply bending moments and get longitudinal strains. Just like very strange sort of stuff going on with that B matrix. All right, we were finishing the last lecture with an example using 045-45-0 laminate, where we had actually start to go through and sort of define some of these things symbolically that will come up in the calculation of the A, the B, and the D matrices. So that's about where I want to pick up. We first went entirely through the A matrix. So we looked at, here's the general equation for the A matrix, and we looked at calculating one of the entries of A. Remember that there are 9 entries of the A matrix since it's a 3x3. So we looked at calculating the 1-1 entry of A, which will utilize 1-1 entries of the various Q matrices that make up the stiffness of the individual layers. And we got to a point that looked something like this. So A11 was some combination of geometric properties, namely the thickness of the sample, here the half thickness of the entire laminate, and then material properties of individual layers. So the stiffness of the Q matrix with 0-degree orientation and the stiffness of the Q matrix with 45-degree orientation. So ultimately we got to a point where we could sort of say that all entries in IJ have this general form, where we have this leading coefficient, which is the half thickness of the piece, multiplied by the summation of the stiffness of the 0-degree layer plus the stiffness of the 45-degree layer. Okay, so that's about where we left off. And I want to pick it up here with calculations of B and D, and that'll sort of bring it home a little bit for some of the long form calculations that we're going to end up doing by hand in this class. All right, we have kind of one more long hand form calculation that we're going to do a little bit later with actual full-fledged numbers. But again, I just want to keep going on this general idea of calculating these stiffness matrices here, because there's some interesting things that'll kind of flesh out when we talk about what the B matrix looks like, and we'll see something interesting happen here when we actually calculate the B matrix for this particular composite. All right, so if you want to pick things up with me, I'm actually on slide 18 of the notes, and that's where we're going to kind of go today. Before I can continue, I don't see any complaints about not being able to hear me or the headset not working, so I'm going to assume that things are all good since no one's saying anything in the chat. So I'm going to keep going. Okay, so there we are. We calculated E. So now we're going to calculate the B matrix. All right. Okay, so for calculating the B matrix, let's write the general equation. So the general equation here, we have that B, don't forget your 1/2. This is a common thing to forget, is the 1/2 leading coefficient that comes actually from the integration. So don't forget that guy. For K equals 1 to N, where N is the number of layers in our laminate. Here we have 4 layers, but we'll come back to that. This is Q bar layer K multiplied by ZK squared minus ZK minus 1 squared. All right, so that's our general equation for B. So let's look at calculating the B11 entry. So we'll just calculate one of the 9 entries of this particular guy. So remember, this is actually 9 equations. just as a reminder. We know it's symmetric, so really we can get away with 6 equations here, 3 along the diagonal and 3 in the upper or 3 in the lower. But you get the general idea that there will be 9 entries of B here. So Bij being ij 1 to 3. All right, so let's look at calculating what would be the B11 entry. All right, so I'm going to actually pull the 1/2 over here and make this a 2B11, 2B11, or not 2B11. Okay, so here 2B11 is going to be, again, looking at the summation, we'll start with layer number 1, then we'll add layer number 2, add layer number 3, add layer number 4, since we have a 4-layer laminate. So here the contribution of the first layer, we're going to have the Q11 entry, Q bar 11, and this particular layer, the first layer, is at the orientation of theta equals 0 degrees, and we're going to multiply that by what would be z1 squared minus z0 squared. All right, so this is again just sort of following this general summation here. And then I'm going to add to that Q bar 11 for layer number 2. That's oriented at theta equals 45 degrees. And here we have z2 squared minus z1 squared. Add to this Q bar 11 for theta equals 45 degrees. This is my next layer, times z3 squared minus z2 squared. And then finally, my last contribution, I have my last layer at 0 degrees, and here I have z4 squared minus z3 squared. And I'll move this over a touch, and there we go. Okay, so that's my general equation there. And remember that we did define these variables z using the actual laminate height h. So remember, we put our coordinate system at the midplane, and we can define z0 through z4 using the full laminate thickness h. So if I kind of go back up here to my picture, remember here's my picture, and I'm defining these variables z0 through z4 using either h on 2, h on 4, so on and so forth. Okay, where here h is the full thickness of my laminate stack. All right, so now I'm going to plug in those values of z0 through 4, and we'll see what happens. All right, so let's move down here. So let's continue. 2b11 or not 2b11 will be here q bar 11 theta equals 0. So it's the 0 degree orientation, just like constantly reminding me of that. And then here now I have z1. All right, so if I kind of scroll back up here, remember that z1 here is negative h on 4. So it's this sort of length right here. So that squared will be positive h squared on 16. All right, so here we have h squared on 16 minus z0. Z0 is at negative h on 2. So this will become h squared on 4. All right, so that is the contribution of like the geometry from that location. All right, so let's continue. We can bang out the rest of these guys. So again, theta is 45 degrees for this contribution. And z2 is at location 0. So 0 squared is, you can do this. I believe in you. 0, good. Minus z1 is at negative h on 4. So this squared is h squared on 16. All right, now we're adding q bar 11 for theta equals 45 degrees. Continuing with our thickness contributions. Here now we have z3 squared minus z2 squared. All right, z3 is at location h on 4. So this will become h squared on 16 minus z2 is at 0 plus q bar 11 for the angle theta equals 0 degrees. This is my last layer contribution. And here this is z4 squared minus z3 squared. All right, z4 is at h on 2. So this becomes h squared on 2 minus, h squared on 4 minus h squared on 16. All right, so this is my full B11 entry. Okay, coffee. Guys drink coffee? Helps the world go round. Ah, good things. None of that like Frappuccino, 15 pounds of sugar stuff. You know, too much for me. All right, so there's some interesting things that kind of happen because of the squares that pop up when we're looking at the thicknesses, like z0 squared, z1 squared, so on and so forth. There's some like negative signs that kind of sort of shift around. And so what ends up happening is that you get a lot of terms that cancel. So let's, for instance, look at, here's this leading coefficient. Here's this leading coefficient. Q bar 1 1 for theta is 0. Q bar 1 1 for theta is 0. Okay, so we have these sorts of things that pop up from what would be the first layer and the fourth layer. All right. And you'll notice here that here we have an h squared on 16 minus h squared on 4 term. And here we have a positive h squared on 4 and a negative h squared on 16. So what happens is there's going to be some canceling here. All right. So positive h squared on 16, negative h squared on 16. Negative h squared on 4, positive h squared on 4. Okay, so what happens is the contribution of this guy, basically, these two guys cancel out. All right, we have a very similar thing that happens with the 45-degree layers. Okay, so here's my 45 coefficient, and here we have a negative h squared on 16 and a positive h squared on 16. All right, so again, these guys will cancel each other out. And so what ultimately results is, for this particular laminate, we're going to end up with B11 is equal to 0. All right, everything sort of cancels out because we have a symmetric sort of condition that when we square things and sort of eliminate the negative signs appropriately, these things end up sort of like canceling each other out, right? So here we see B11 is 0, and we can generalize this to say like Bij is 0. Okay, so for this particular laminate, all Bij is 0. And we'll talk about this a little bit more, but this really is a result of the symmetry of the laminate. So this is because of symmetry about midplane. Okay, so we'll come back to this a little bit more, and we'll characterize some special laminates moving forward, a symmetric being one type of special laminate. And with some of these special laminates, you can really simplify your calculations of, let's say, the A, B, and D matrices if you know some specific things about the laminates. All right. Okay, so that's the B matrix. Now we'll calculate the D matrix. All right. So the D matrix is also going to be it's going to be sort of revealing to us as well. All right, when you think about the D matrix is the matrix that tells us how stiff the laminate is for resisting bending moments. All right, now when you think about the application of a moment and the resulting stiffness that comes up from some material that you may be bending, we know that generally material far away from the midplane is going to help us resist the bending. All right, this is the basis for like why I-beams are so effective, okay? Because they have a lot of material far away from the surface to help us resist that bending moment. Sort of a property of the moment of inertia of the piece, right? So if you can put most of your material far away from the axis of bending, you can resist a significant amount of bending. So we're going to see some reflections of that here when we see that the contributions to the D matrix from the stiffness are going to be heavily influenced by the outer layers of the composite and not influenced nearly as much by the layers closest to the center of the composite. And that's because when we're enacting bending, the material farthest away from the midplane has the most influence on how the stiffness or how that material will react. Okay, so let's hope that the math shows us that phenomena. Okay, so let's write the general equation then here for the D matrix. All right, so I'll write that here. Recall that D is, don't forget your 1/3 coefficient. The summation from K is 1 to N, where N is the number of layers of Q bar K. And here we have ZK cubed now minus ZK minus 1 cubed. All right. So let's work through D11 just like we've done, and then we'll extend that generally to Dij. All right, so to calculate D11, and again, I'll take the 1/3 to the left-hand side. So I'll make this in 3D. Okay, 3D11. And let's just bang it out again like before. So here we have Q bar 11, the contribution from the first layer for theta equals 0. And here now we're multiplying by Z1 cubed minus Z0 cubed. This is ZK minus 1. All right. We're going to add to that the contribution from the 45 layer. Here we have Z2 cubed minus Z1 cubed. All right, no sleeping. Wake up. All right. Plus Q bar 11. Here theta equals 45 degrees. This is Z3 cubed minus Z2 cubed. Plus, finally, the last layer that contributes, theta equals 0. And here we have Z4 cubed minus Z3 cubed. All right. So hopefully we're sort of getting used to this now. The reason, again, I'm kind of beating this to death is I want you to see the summations. I want you to see how they're expanded. I want you to see the math. Just sort of helps lock it in there. All right. So we can, again, plug in for Z1, Z0, Z2, so on and so forth. And you're going to end up with the following. I'll just sort of pick up the pace here a little bit. Q bar 11 for theta equals 0 degrees. And here, if I do my Z1 cubed minus Z0 cubed, I'm going to end up with negative H cubed on 64. Here, plus H cubed on 8. All right, the plus comes in because I have a minus and negative. All right. Then this will be plus Q bar 11 for theta equals 45 degrees of Z2, which is 0, minus Z1 cubed. So it'll be minus a negative H cubed on 8. So this will be plus H cubed on 8. Now here we have a plus Q bar 11 of theta equals not 0. We're still at the 45. So this is contributions from the third layer. I'm going to have very similar looking. So H cubed on 8 minus 0. All right. And finally, we have plus Q bar 11 for theta equals 0 degrees. This outer layer for what is Z4 cubed minus Z3 cubed. So this will be H cubed on 8 minus H cubed on 64. All right, how are we doing? No questions? No questions? Because everybody is sleeping. Wake up. Okay. All right, so we can pull like a common factor out of this because we have like 64s and 8s and all this sort of stuff hanging out. I'm going to pull a common factor out of here, which will look a little bit strange, but it'll be 96. And you'll see that there's H cubes everywhere. All right. So let's not do 96. Let's do really, we can probably pull like a 32 out here. All right, so I'm going to do that. So I'll keep the 3 over here. This will be H cubed on 32. And here we will end up with some contributions from this guy. So the Q bar 11 coefficient is going to be some number, and the Q bar 1145 coefficient is going to be some number. Okay, so here and here. All right, so the contribution from this guy and this guy together will be a total of 7, which is a little bit strange. So 7 q bar 1 1 times for the condition for theta equals 0, plus my coefficient here will be 1 q bar 1 1. 1 you can leave in or leave out. I'll just take it out because it looks a little bit silly to me. Q bar 1 1 theta equals 45 degrees. All right, so finally, if I pull the 3 to the other side, I'll end up with d11 is h cubed on 96, 7 q bar 1 1 for the contributions of the 0 layers, plus 1 relative contribution of the 45 degree layers. All right, so here's d11, and generally we can show that this is true for all dij. So generally, this holds for all dij, such that for this particular composite, dij is h cubed on 96 multiplied by 7 times the contributions from the 0 layer plus 1 times the contribution. Sorry, this should not be 1 1. This should be ij. One times the contributions from the 45 degree layer. All right, so what can we learn from this exercise? Okay, so what we see here is that for this particular laminate, there's some leading coefficient, some geometric term here that is driven by just the thickness of our general piece, okay? That's this h cubed on 96. But what's also interesting to note is that we have coefficients in front of the contributions from the various layers, okay? So look at these two guys here. The contributions from the 0 layers here have a coefficient of 7. The contribution from the 45 layers have a coefficient of 1. That means that the contribution to the D matrix from the outer layers, which are these 0 layers, is 7 times more important than the contribution from the inner layers, which is these 45 degree layers. So this shows you that even though they're all the same thickness, we have a lot more contribution from the outer layers of the piece just because of the way that bending works, okay? We know that material farther away from the neutral axis of bending will contribute more to the stiffness or the general stiffness of that piece, okay? So this is why I-beams work. This is why sandwich composites work, okay? You have the stiffest material in a sandwich composite far away from the center of that composite. You're increasing the bending stiffness while relatively increasing of the weight or the mass of the piece by a very little amount, okay? This is why sandwich composites work well. This is why I-beams work well. Okay, this is why you want your stiffest material to be on the outside edge of the piece. That's why you might see face sheets associated with composites as well. That's why this crappy IKEA desk that I have has particle board in the middle and veneer on the edges. Okay, that's exactly why. All right, so the relative contributions of the layer, important here. All right. How are we doing? Any questions? Nope, don't see any questions. All right. Is anybody even still here? Yeah, lots of people here still. Okay, well, if you're awake, I don't know. And Travis is here. Damn, he's in California. Okay, good job, Travis. Okay. So that's kind of what I wanted to show with this example. I'm going to pull up the PowerPoint slides here just for a second so we can talk about some specifics of this laminate that I'm going to show that I don't necessarily need to write out in full form on the whiteboard. Okay, so I'm going to stop sharing my white pad for a second, and I'm going to bring up the PowerPoint slides. Okay, so we saw in this last example for a symmetric laminate, right? So remember that our laminate looked something like this up here. So it's 0, 45, 45, 0. That means that the layers are symmetric about the midplane, okay? So if I go 1 below, it's 45, 1 above, it's 45. 2 below, it's 0, 2 above, 45, okay? It's kind of a symmetric laminate. So if that is the case, we saw that the Bij matrix was 0. And so that means that generally all the entries here of B matrix in this full 6x6 laminate stiffness matrix will be 0. And that generally means that we could simplify for a symmetric laminate to decouple the 6x6 into two 3x3s. Okay, so if you just think about general matrix math, you'll have the n's times the a's plus the n is equal to a times epsilon plus b times kappa. Well, if there's no b, then n is just a times epsilon, which is this general equation here. Decoupling this matrix entirely, and M also can be decoupled in the bottom by eliminating the B matrix. So what this means is that for symmetric laminates, if we have a symmetric system, that if we pull longitudinally on this particular guy, we're only going to get longitudinal strains. And if we apply bending moments, we'll only get curvature. We're not going to get any extension. So we've eliminated any coupling by having a symmetric matrix or a symmetric laminate. And this is why symmetric layups are so common. Okay, and that's because it eliminates any potential craziness that might come up from the coupling of applying longitudinal loading to curvatures that might develop, or applying a bending moment and getting longitudinal strains. Okay, so we saw with this symmetric layup some special things happening, namely in this particular situation that the Bij matrix was 0. So because we could identify that this laminate was symmetric, if we know that all symmetric laminates have Bij equal to 0, then we can really simplify our calculations going forward, cut down on calculation time, and generally understand physically what's going to happen with our laminate a little bit better. Okay, so there are other special types of laminates as well. So we talked about the symmetric type, but we might have a cross ply, we might have a balanced angle ply, an anti-symmetric, or a quasi-isotropic. So I'm going to explain what each one of these things is in just a second, and we'll talk about the reductions that you might have for calculating the A, B, and the D matrices given these general types of laminates. All right, so if you know you have a special laminate, you can significantly cut down on your calculation just by saying, all right, it's symmetric, Bij is 0. I'm not going to go through the whole rigmarole and try to calculate it. I'll just write on my paper, Bij equals 0. Okay, those of you that took the final the first time around, you should have done that, but many of you didn't. Okay, so let's talk about the special laminate types. All right, so here I will just lay them out on these slides and we'll talk about them briefly. So a symmetric laminate, that's the one we just kind of worked on, and you saw here that the ply sequence is a mirror about the midplane. Okay, so if I go down 1 from the midplane and I go up 1 from the midplane and they're the same value of theta for my stacking sequence, it's a symmetric laminate. That is for all the layers. If you have a symmetric laminate, all Bij is equal to 0, and so we don't have any of this bending, stretching, coupling. What I mean by that is if I pull on it, there's no curvature, and if I apply a bending moment, there's no longitudinal strain. All right, so that's the first type of special laminate that we have. And this is a very common type of laminate for people to sort of manufacture it in this way. Now, the laminate that we made in class was not symmetric. Okay, we had a 0,595 laminate. That ain't symmetric. All right, so I purposefully picked that stacking sequence because there's crazy things that happen when you don't have a symmetric stack. Okay. All right. The next laminate I want to talk about is the cross-ply laminate. Okay, so a cross-ply laminate is a special type of symmetric laminate in which all the layers are either 0 or 90. Okay, so a cross-ply laminate contains only 0 and 90 plies. So when you have only 0 and 90 plies, there's no real shearing, coupling, shearing, stretching that occurs. Okay, so what I mean by that is a lot of times if we saw this for lamina. If you pull on a lamina, it might have a tendency to shear in the plane. Okay, so pulling the lamina might give you gamma XY. All right, same thing as if you try to shear a laminate in plane, it might extend. Okay, this is different than the whole laminate pulling and curving out of plane. Okay, so there's a difference here between the coupling of the longitudinal tension and the shearing strain that might develop, and the difference between what is pulling on the laminate and it curving out of plane. All right, so that motion, pulling on it and curving, is associated with the B matrix, whereas the pulling and shearing is the coupling or the relationships of A16 and A26, as well as D16 and D26. All right. So if you have a cross-ply laminate, A16, A26, D16, D26 equal to 0. Okay. So this is no stretching, shearing, coupling. Next, balanced angle ply, very similar. For every minus layer, there is a plus layer. Here, this happens to be a symmetric balanced angle ply, but it doesn't necessarily have to be symmetric. You could have negative theta, positive theta, positive theta. That is still a balanced angle ply, though it is not necessarily symmetric. All right, anti-symmetric laminate. This is a mirror of every theta about the midplane being a negative theta. And I want you to keep in mind that 0 and 90 are like positive and negative theta. Okay. So if this is the situation, you have A16, A26, D16, and D26 equal to 0. And then many entries of B equal to 0. Really, the only entry of B not equal to 0 here is the B16, B26 entries. All right. Lastly, and we're not going to cover this in too much depth, I'll kind of gloss over it, but lastly is the quasi-isotropic laminate. And the quasi-isotropic laminate is interesting in that it truly isn't isotropic, but it sort of behaves that way. And you sort of mathematically sort of hand wave and say, all right, if we have enough layers stacked in this particular composite such that we're sort of like accommodating all directions equally, then we can have more or less equal properties in all directions. That's kind of the assumption here. So any stacking sequence which eliminates angular dependence on the calculation of Aij would consider yourself quasi-isotropic. All right, if that's the situation, here's the general relationship for isotropic materials. Okay, so we talked about an isotropic material having only two constants. And so here in this situation, the A matrix would only have two independent variables, A11 and A22, for instance. Okay. All other Aij 0, almost always symmetric, and typically it's some variation of plus minus 45s and 090s, or some combination of 30-degree orientations, right? 0, negative 60, 60, 60, negative 60, 0, or 0, 30, 60, 60, 30, 0, something along those lines would be kind of considered quasi-isotropic. All right. So the next set of slides actually goes through the derivation of all of these special cases. That is, here's an example of calculation of Aij for a cross-ply. Here's Bij for a cross-ply, and Dij for a cross-ply laminate. It's just like the example that we did for the symmetric laminates, all right, except kind of showing them full force. Here's the derivation for the simplifications for a balanced angle ply for all of the situations, Aij, Bij, Dij, so on and so forth. I'm not going to go through all of these. I just want you to be aware that they're there if you want to see how we sort of derive these special relationships, okay? Here we are for anti-symmetric, Aij, Bij, Dij, so on and so forth. Okay, so I put all of those there, and it actually took me a really long time to put those slides together, and I glossed over them for 10 seconds, but such is the life of a teacher, I guess. I put all that information there if you want to just take a gander at it and sort of see what the differences are between those special laminates. But in short, I summarized it on this slide and this information, which is also in your equation sheet, to talk about identification of special laminates, what they look like, and the resulting entries of the A, B, and D matrices, which sort of go away if you can say that it is a special laminate. Okay, so this is the general summary for things like symmetric, anti-symmetric, unidirectional, cross-ply, angle ply, balanced angle ply, quasi-isotropic. All right, so it sort of describes what they are, and then if you can identify it's symmetric, then you come to this side and say, okay, if it's symmetric, all Bij is 0, which is sort of the first thing that we showed today. If it's balanced, you have this, symmetric, balanced, so on and so on, so on and so on. Okay, you get the general idea there. All right, so I think I'm going to call it today. I wanted to go through an example problem with actual numbers, So I think I don't think I'm gonna have quite enough time to get through it. So instead of kind of rushing to get through it, I think I'm just gonna call it here, and we'll pick up this example on um, on Wednesday. One last thing I'll say is I did post your homework, and you actually should be able to get through numbers 1 and 2 on the homework. And there's actually only 3 problems on the homework. So if you got extra spare time, which let's be honest, you're not going anywhere anyways. Um, if you have extra spare time, you can actually get going on the homework. Okay, so you should be able to get through numbers 1 and 2 on the homework now after we've discussed how to calculate A, B, and D. All right. So that'll do it for lecture today. Get you out a little bit early, but again, I want to make sure I have a little time at the end of every lecture to get feedback about how my mic is sounding and if you guys if things are going okay, so on and so forth. So that'll be it for today. If you want to take off, go ahead. Otherwise, I'll stick around if people have questions in the chat.